Let's take a look at atomic spectra. Atomic spectra are created when an electron absorbs or emits energy as it moves around in an atom. Energies that are absorbed by an electron allow it to move to higher energy level orbitals within the atom. This is something that you should have learned in first year chemistry. And then what this means in terms of quantum mechanics is the electron can only move to a higher energy level if it absorbs a certain quantity of energy. If it doesn't absorb enough, it may jump up a little bit, but it's not going to reach the next energy level, and it will fall back to where it's starting. This also means that when an electron is giving off energy, when it's falling from a high energy orbital to a lower energy orbital, it can only give off a certain amount or quantum of energy. That allows it to fall to the next energy level or 2 energy levels down. So there are only specific quantities electrons in a given atom can absorb, and only specific quantities of energy they can emit. And Niels Bohr discovered this and used it to relate energy of electrons to the atomic spectra that he observed by looking at various elements. If I shine a continuous visible spectrum, basically that means white light, and I shine it through a transparent but colored liquid or substance, what I'll see is the rainbow spectrum, but I'll see some black lines like this. And these are places where the electrons have absorbed energy to allow them to jump to higher energy levels, and so all that energy is removed from the spectrum, leaving the black lines. As you might guess, this is called a black line or absorption spectrum. So the absorption spectrum, again, is created by electrons absorbing energy to jump to higher levels. If electrons jump from high energy levels to lower energy levels, these produce bands of colored light because energy is associated with wavelengths and frequencies. And if they're in the visible spectrum, we can see them. Here are 2 examples of emission or bright line spectra. They are created when electrons fall from high energy levels to lower energy levels. If you take a look at these 2 emission spectra, bright line spectra, the top one is helium. We have a red band of light, we have a yellow band of light, 2 blues, indigo, and an almost violet band of light. Not that many. If you think about helium, it's a fairly basic element. It has 4 nuclear particles, 2 protons, 2 neutrons, and 2 electrons in the shell surrounding the nucleus. So with only 2 electrons, it stands to reason that you're not going to see a whole lot of bright lines in its spectra. The bottom bright line spectrum is uranium. It's a lot more colorful. I would like you to think about and come up with the reason that you think uranium has so many more lines in its bright line spectrum compared to helium. Again, Niels Bohr is the one that identified the relationship between a visible spectrum and the energy level transitions that the electrons go through. He used Planck's equation, and that helped him to relate energy to frequency and then to wavelength of light that he saw as the electrons move from one energy level to another. So here we have the hydrogen spectrum. It has 4 bright lines, 2 purple, a turquoise, and a red. And what he determined through experimentation and mathematical calculations is these bright lines are all due to the fact that electrons jump from higher energy levels, so energy level 6, 5, 4, and 3, and end up in energy level 2. Now, if you know anything about the hydrogen atom, if you remember anything about your chemistry, you'll know that the electron in hydrogen, when it's at its most stable state, is in the ground state. And the electrons do eventually fall there. But in this case, if I want to see the bright lines, they will stop at n equals 2. So when the electrons fall to n equals 1, more energy is given off. And what this does is it takes the spectrum from the visible up to the ultraviolet. So using Planck's equation, we can look at the energy involved in the electron transition from one energy level to another one. What we're looking at is the change in energy is what creates the frequency of light or the wavelength of light. So those are the equations we're going to look at. Each energy level, the electron possesses its own energy there. And so change in energy is equal to the energy at the final position minus energy at the initial position. Again, this is an illustration of looking at quantum physics as opposed to classical physics. The electrons can't change position, their energy level, their distance from the nucleus, unless they gain a specific amount or lose a specific amount of energy to allow them to move between specific energy levels. Think of it as walking upstairs. You have to lift your foot a specific height to get to the next step, as opposed to just shuffling along if you are walking up a ramp. Bohr came up with this equation to relate the energy he saw based on the wavelengths of light from the emission spectrum to the energy levels that the electrons were moving from or moving to. And in the equation, E is for energy of the electron in a particular energy level. So Z is the atomic number, and that's the number of protons. In hydrogen, that number is 1. N is the energy level. N equals 1 is ground state for hydrogen. When an electron is completely removed from an atom, N becomes infinity, and the energy for that electron is 0 joules. Let's take a look at an electron falling from N equals 6 to N equals 1 and see what sort of energy change is created. N equals 6, the energy is going to be, the equation again is negative 2.178 times 10 to the negative 18 joules. Z for hydrogen, atomic number is 1. And we're starting at N equals 6, so it's going to be 6 squared. So we punch all that in and we get a negative 6.05 times 10 to the negative 20 joules. We'll do the same thing for N equals 1. And the energy there is going to be, again, same equation. Here N equals 1, so it's 1 over 1 squared. So we just get negative 2.178 times 10 to the negative 18 joules. Now the change in energy is what goes into creating the color of light that we see. The wavelength and the frequency of light we see is associated with a change in energy. And so that's going to be the final energy, N equals 1, so negative 2.178 times 10 to the negative 18 minus our initial energy, negative 6.05 times 10 to the negative 20. So our change in energy is negative 2.12 times 10 to the negative 18 joules. And if we use the hc over lambda or the hf equation, we can figure out the frequency associated with that energy, or we can figure out the wavelength associated with that energy. Something that's important, and usually the negative sign is left off, but the larger the negative number, so here we've got negative 2.12, here we have negative 2.17, and here we have negative 6.05, but it's to the negative 20. So the larger the negative number, the more stable the electron is. So if we compare these two values of negative 2.178 times 10 to the negative 18, negative 6.05 times 10 to the negative 20, this is much more stable because it's a larger number. Negative 18 is a larger value than negative 20. So the overall generic equation, if you don't want to do the energy for the electron at each energy level, looks like this. A change in energy equals negative 2.178 times 10 to the negative 18 joules, and then it's 1 over final n value squared minus 1 over initial n value squared. If you put in a positive energy here, then you need to make this positive as well. If you don't do that, you're going to get weird answers. Bohr and Planck and other physicists at the time had already established that light had wave properties and particle properties. Wave properties because they could measure wavelengths. Remember, particle properties because they saw how light could knock electrons off of metal, so essentially the photoelectric effect. Since the photons could do that, knock electrons off of a metal, they possess momentum. Momentum is the mass of an object times its velocity. And photons theoretically don't have a rest mass. This leads us a little bit into relativity and special relativity, because those theories say that the faster something goes, the more massive it becomes. So if we have these photons traveling close to or at the speed of light, they are actually going to possess some very tiny amount of mass. So the equation that we're going to give is P is the symbol for momentum. So that equals the mass times the velocity of my photon. And it turns out that that equals h over wavelength for photons. Okay, de Broglie used this equation in Einstein's energy equations and said, well, if it works on light, maybe it works on matter. And so the same idea for light, that it could behave as both a wave and a particle, was applied to matter. And this was described then as the wave-particle duality of matter. in addition to light. And so de Broglie came up with a wavelength for matter using the equation for momentum of a photon and changing it so that mass was something measurable, that of an electron, that of a proton. And the equation for the wavelength of matter looks like this. Wavelength equals Planck's constant over the mass times the velocity or the momentum of an object. So it turns out that the momentum equation is true for both photons and electrons. Electrons are about the smallest particle of mass that this works effectively on. Anything bigger than an electron, even looking at protons and neutrons, they're actually too massive. You might remember that protons and neutrons are about 1,000 times more massive than electrons. So if I can have a particle that has mass, that has a wavelength, then apparently it can also have a frequency. So the frequency of matter, according to de Broglie, is simply the same equation, the energy over Planck's constant. And we just took that energy equals h times f and rewrote it.